Thank you, Cyril. Do you hear me? Does it work? Yeah?
Yes.
Yeah? So, thank you for the kind introduction, and I would like to thank the organizers for inviting me here. It's a pleasure. This talk is in some sense linked to the previous two plenary lectures because I will try to show, as Cyril advised yesterday, that it is possible to look at the infinity in different ways, different with respect to the usual ones we are used to do. And second, Professor Wang was speaking about the future computing, and for certainly this kind of computing, infinity computing, will be one of these new ways of doing. So people usually are afraid of infinity. For example, Jorge Luis Borges has written this phrase. He has dedicated a lot of space in his stories to infinity. And you see that people are afraid of infinity, but we will be brave, we will not afraid, and we try to manage infinity. And what is important, not during the eternity. We would like to execute practical computations, and for this we will need some practical devices. So I will speak about a new computational approach to infinity, which has resulted already in 3 patents in Europe, in Russia, and United States. Then we have organized 2 international conferences, and a number of special issues in the journals with very high impact factors have been published and are in preparation. Then I should say that there exists this internet site, and we have published this small book written in a popular manner, and I have some copies from the publisher here with a special discount for this conference. Then I should say that this new approach has been accepted very well by the community, because I have got a number of prizes in various countries. Here there are only some of them, and we continue to work in several directions. So this was the advertising part. Now let's go to our business. No, there is another advertising part, because this is an article from MIT Technology Review that has been published recently, dedicated to my research on Sierpinski carpet. Okay, so we should remember that people thought about infinity for centuries and for thousands of years. For example, Aristotle was the first person who has introduced the difference between potential and actual infinity. Then, of course, we should mention Leibniz and Newton for introduction of infinitesimals, Abraham Robinson for his non-standard analysis introduced in 60s of 20th century. But the modern history of infinity starts with Georg Ferdinand Ludwig Philipp Cantor, who in 1873-74 has published a number of papers showing that there exist different kinds of infinity. Okay, it is necessary to say that Cantor's ideas have not been accepted very well initially. It was immediately a fight. For example, Poincaré was strongly against his approach, but Hilbert was strongly pro his approach. And probably because Hilbert lived 30 years after Poincaré, this approach of Cantor now is a tradition. But Poincaré told that this approach is some kind of the childhood illness of mathematics. It is necessary to mention here also that these big mathematicians were from different scientific schools, and the views on mathematics and natural sciences were different. Because Poincaré thought that mathematics is a part of natural sciences. It has strong links with physics, with engineering, and so on. And Hilbert proposed his famous program for mathematics, very abstract level, something like the queen of all sciences, and so on. And nowadays, this point of view is the dominant in the mathematics. However, I would like to say that my talk is closer to Poincaré because I am a mathematician and a computer scientist, and so I would like not to speak about abstract things, but I would like to make computations, practical computations, with different objects. And we will see that it is possible to look on all this kind of stuff, infinity, infinitesimals, in different ways, closer to the natural sciences. Now, all of you know that computers work with only finite numbers because there exist undeterminate forms. Infinite numbers often are represented as infinite sequences, and there are technical problems how to put an infinite number in a finite memory of the computer. So these crucial difficulties did not allow us to organize the computational process with infinity numerically. Sometimes in some languages you can put symbols, some symbols related to infinity or infinitesimals, to work of them. And our first goal will to construct a computer that is able to work with infinities and infinitesimals numerically. Then, usually when mathematicians deal with infinite objects, it is supposed that human beings are able to execute certain operations forever and execute infinitely many operations. You have seen many times in the books of mathematics 1, 2, 3, and so on, and people think and suppose that they are able to go to infinity. But of course, this is an abstraction because we live in a finite world, and more or less we would like to see what will be the end of the operation we have started. So this is very important to this applied way of doing, and we would like to make applied computations. We would like to calculate. For the whole talk, there will be very important to remind what is the difference between numbers and numerals. So, a numeral is a symbol or a group of symbols, and a number is a constant that is expressed by a numeral. For example, you see this is one numeral, this is another numeral, this is another numeral, but all of them point to the same number, to the same concept. So we can write down numerals, erase numerals, but numbers are concepts we cannot work. In some sense, as in physics. So in physics, you have the object of the study, the instrument, and yourself, a researcher, and you are not able to touch directly the object. You need an instrument, a tool, to observe the object. So numerals and numeral systems in general are our instruments, our tools to observe numbers and objects we construct with numbers. Now, there exists a lot of difference with the numeral system, numerals that we use for finite numbers, for working with finite numbers, and with infinite or infinitesimal ones. So the finite numerals, the same finite numerals, are used for different purposes. For example, we can say that 5 is the number of the chairs around the table, and 5 is the number pointing the order in a sequence, and so on. With infinity, everything is different, because we use different symbols in different situations. For example, this is the lemniscate symbol introduced by John Wallis, and we use in analysis. Then omega is for working with Cantor ordinals, alephs for dealing with cardinalities, countable, non-countable, and so on. Then there is non-standard, there are non-standard numbers using generic infinitesimals. So there is many of them, and people use them in different situations. We would like to make the situation the same like in the finite world. So we would like to introduce some numerals that can be used everywhere. Okay, now let us return to numeral systems that we will use to express finite numbers. And it is necessary that there exist plenty of them, and all of them are different. And all of them, this is important for computations, have different power. For example, the positional numeral system is the most powerful numeral system we know. But in order to express irrational numbers, what do? We are not able to use and by a finite number of symbols to write down the quantity expressed, for example, for pi. What people do? They introduce a special name, a special symbol to indicate this point. And for all rational numbers, they do the same. So square root or something like this. So positional system is not able to express these numbers. Then Roman numerals are very popular, but probably we do not remind every day that Romans did not have symbols to express 0. And for them, this operation was an undeterminate form. So what we can see from here, we can see that introduction of the powerful numeral system, has a positional one, has allowed people to solve once and to forget about undeterminate forms of this kind. So stronger numerals, stronger instruments allow people to see more and to work easier. Because, for example, in Roman numeral systems, the operations of division and multiplication are extremely complex, extremely difficult. And at centuries ago, when there were no positional system, only the most brilliant thinkers were able to work and to divide and to multiply. Okay, but probably you know that there exists even weaker numeral system. For example, this is the unary numeral system, where the numbers are represented by strokes or by stones and something like this. It's clear that it is difficult to work with this numeral system. First of all, it is difficult to express large numbers, because when you start to put strokes, then you will make errors first. Second, nobody knows how to multiply and to divide using these numerals. So different instruments allow us to calculate and to compute easier or harder, and there are some numerals there are some numbers for each numeral system that cannot be expressed in one or another numeral system. This is very important. Why? Because this means that the most strong numeral system people have in each historical period, it limits the possibility of computing. It limits the possibility of writing down mathematical theorems. The Romans were not able to write down one theorem about negative numbers. They did not know about them. So numeral systems are very important for the human development. And of course, numeral systems are just a small part, an example of languages. We all know how languages are important for the human development. Strangely enough, there exists another, even weaker numeral system than this one. I am speaking about the primitive tribe of Piraha living in Amazonia nowadays. So they live in a primitive way, and they use only this numeral and this numeral to represent numbers 1 and 2. For them, all numbers that are larger than 2 are just many. And so the operation 1 plus 2 and 2 plus 2 give the same result, many. Pay attention that many is not a wrong result. It is a correct result, but with the low accuracy. For example, if you ask me how many chairs or people are here, I will answer immediately many. This is a correct answer, but the accuracy is very low. Why I'm speaking about? Because they, Piraha, have a very interesting property. Look, many plus 2 is equal to many, and many plus 1 is equal to many. And now substitute many with the usual symbol of infinity. And what do we see? We see that our views on infinity are the same as Piraha have to the numbers 3, 4, 5, and so on. But we know now that 3, 4, and 5 exist. And probably the question is not of this this kind of stuff of paradoxes and so on is not related to the nature of infinity, but is related to the weak tools we use to express infinite and infinitesimal numbers. And if you think that this is too easy, too simple, I would like to give you another, to present you another tribe living close to Piraha. They called Munduruku, and they have two infinities. Some not many, and many really many. They are able to count up to 1, 2, 3, 5, and then these approximations. And what is interesting, because they have the same arithmetic as Cantor's countable and uncountable. And this is really shocking. At least for me, it was when I have discovered this kind of stuff, it was shocking. So, a small observation, probably our difficulty in working with infinity is not connected to the nature of infinity, but is a result of the inadequate numeral systems used to express infinite and, of course, infinitesimal numbers. So we should direct our forces in inventing new numeral systems that would allow us to work with infinities easier. So let us, it's clear that what I am saying is far away from the traditional abstract, absolute idealistic views of infinity that we have now. So I would like to precise my methodological positions, and these are positions of an applied mathematicians close to positions of Poincaré. First of all, we postulate existence of infinite and infinitesimal objects, but accept that human machines are able to execute only a finite number of operations. So this is not the traditional view, because traditionally people suppose that also people are able to execute an infinite number of operations. And this is not finitism, the famous mathematical theory, because here we are finite. Why we are finite? Because we would like to observe the results of computations. We would like to see the results. Then, in natural sciences, when a person observes in a microscope two dots, he or she does not say that the object of the observation is two dots. He or she says that this lens, this microscope, show us that we can see through this instrument. If we put another lens, stronger ones, probably instead of one dot we will see 10 smaller dots, instead of another dot we will see 15 smaller dots. So again, 10 and 15 dots is not the object, but is the result of the observation. Now pay attention, this means for us many important things. First of all, we will see on the mathematical objects in the same way. We will construct stronger instruments. But what do we say? We say, similarly to physicists, that in the mathematical theorems, the truth is not absolute. It is related to the accuracy and to the instrument we use to observe it. In our example with the microscope, which result is correct? 2 dots or 10 and 15 dots? Both results are correct, but with different accuracy. This is very important. So the same happens for mathematics, because in mathematics, the result of Piraha many is correct, but the accuracy is low. The result, for example, 21 is also correct, but the accuracy is higher. Okay, and finally, we have already seen that this situation is the result of an inadequate way to represent infinite numbers. So we should invent something where we should have this. And we use the ancient Greek principles, the part is less than the whole. In reality, this is nothing else but the Euclid's common notion number 5. So we will apply it, and we will apply it to all numbers, finite, infinite, and infinitesimal, and to all sets and processes, finite and infinite. Okay, so this is our methodological position, but if we have declared what we would like to do, then it is necessary to say how we would like to do. And now I would like to show you a way of counting that people used and continued to use for thousands of years, but strangely enough, this way of counting has not been formalized yet. And we will do, of course, it. So this is the key example. Suppose that we are in a granary, and the owner asks us how many seeds there are in the granary. Of course, we are not able to count seed by seed. They are too many. And what people do to solve this problem, they take sacks, fill them in with seeds, and count the number of sacks. Of course, we suppose that all seeds are equal and all sacks are equal, and sacks are so huge that we are not able in a reasonable in a reasonable time to count how many seeds there are in them. Then, if the granary is also huge, people take trucks, big train wagons, and then at the end we obtain a result in this way. So our granary contains 17 train wagons, 12 trucks, 15 sacks, and 54 seeds of grain. Look, now, if I add one seed, I see that I have more. If I subtract one truck, I see that I have less, and I can measure these subtractions and additions. Of course, I could say that the granary has many seeds. This is a correct answer, but its accuracy is low. Now, what have we done here in this example? First of all, people in this example were forced to behave themselves like they were in front of infinite quantities. And what did they do? They introduced new units of measure: sacks, trucks, train wagons, etc. And the answer that it was impossible to formulate with high accuracy in the elementary units is perfectly answerable in the new units of measure. Then, we do not count in this example how many seeds there are in the sack, how many sacks there are in the truck, how many trucks there are in the train wagon. We know that this number is the same, so all sacks contain the same number of seeds, and so on. And in spite of the fact that this k is not known, we are able to express the correct answer with the accuracy one seed. So now it's clear what I would like to do. I would like to move from the huge but finite quantities to infinite quantities using this new way of counting, introducing new units of measure. Okay, so now pay attention that now we take another road. So the classical road, countable, uncountable, alephs, omegas, all this stuff is on one hand, and we go to another hand, because we should introduce new numerals, new symbols in the same way. Roman numerals are not used in the positional numeral system. There we use new rules, we use new numerals to work with them. And we should introduce our new numerals and new operations, exactly similarly as it has been done to move from the Roman numerals to the Arabic or Indian, Babylonian numerals in the positional system. So, but I would like to say that there will be no any contradiction with the classical results. The situation is exactly the same as in the microscope with two lenses. We will have Cantor lens with one accuracy and our lens with a high accuracy. Both results will be correct, but with different accuracies. Okay, now, what will we do? We introduce a new numeral, this one, called gross one. In Italian, there are here some Italian people, grossone, è un simpatico modo di esprimere. So, this is a gross unit, and we introduce it as the number of element of the set of natural numbers. And this will be a new axiom added to the axiom of real numbers. And if you think, thank you very much. If you think, then the passage from Roman numerals to the positional numeral system was exactly the same. People have introduced a new symbol. this one. They said this is a new number, and we should work with this like this and this, and so on. And then the operations have been introduced. So I will introduce gross 1 as the number of elements of the set of natural numbers. And a new symbol which is introduced as the totality of objects is already used. For example, in the theory, probability theory. We have the space of events, omega, and we work with this space of events. Okay, so let us see the properties of the gross 1. First, gross 1 is an infinite number, so it is larger than any finite natural number. Then it is a number, so we have this, and all of this kind of stuff. I just have written this here to emphasize that in new analysis, mathematical analysis, we will not have indeterminate forms like infinity minus infinity. This is a complete analogy to the passage from Roman numerals again to the positional ones, where in Romans 3 minus 5 was an indeterminate form. And here we have extended our language and we will be able to say more. Now, the third part of the axiom is the most interesting. So this is the set of natural numbers, and we have postulated that it has gross 1 elements. Think about gross 1 as like about number of seeds in your sack. So the set of natural numbers is our sack, and it has gross 1 seeds. So we postulate that our sack can be subdivided in 2 equal parts. Look, I am not able to calculate 1, 2, 3, 4, and so on. Why? Because my first postulate told me that I am able to execute only a finite number of operations. And these sets, both of them, they are infinite. I apply here in the strong form the third postulate. The part is less than the whole. I say that I do not know how seeds there are here. I do not know how seeds, I am not able to count them. I'm not able to count the number of seeds in the half of the sack, but I can say that in the half of the sack, I have 2 times less seeds than in the whole, okay? Now, but I also can postulate, and I do this, that in the third part of the sack, there are 3 times less seeds than in the whole sack. Look, these sets are very useful for us. What is this? This is the third part of the set of natural numbers, starting from 1. 1 plus 3, 4, 4 plus 3, 7, and so on. What is this? This is the third part, starting from 2. 2 plus 3, 5, 5 plus 3, 8, and so on. This is the second part, starting from 1. 1 plus 2, 3, and so on. So I have many sacks, and I will start to count. I will start to distinguish the number of elements in different infinite sets. And of course, I can postulate that for any nth part, these sets are equal. So I subdivide my set of natural numbers in equal parts. Okay, and now I can start. I can start computations. Look, how many elements there are here in this set? Very easy, because this is the fifth part starting from 2. 2 plus 5, 7. 7 plus 5, 12. So we have this number of elements. And what is this? This is the 10th part starting from 3. 3 plus 10, 13 plus 10, and so on. So it has this number of elements. And I can execute theoretical set operations with them. Look, how many elements there are here? Pay attention, I do not use more the word cardinality, because I am able to calculate the number of elements exactly. So here, very easy, this is the answer, and this is the proof. So these 2 sets, it is easy to show that the intersection is an empty set. Then I have added 2, but it is here. I have 3 is here. So I have added 2 new elements, but exactly this is written here. So I can compute the number of elements of these sets. But in reality, it is possible to calculate even more complex, a lot of more complex sets, and it is possible to write down new numerals and to interpret them. For example, what is this? From the point of view of the seeds, this is the number of seeds in a sack from which we have subtracted 2 seeds. From the point of view of the set theory, this is the number of elements in the set of natural numbers from which we have subtracted any two numbers. And what is this? This is the number of seats in 6 tracks minus 2 sets plus 3 seats. In order to understand what is, from the point of view of set theory, it is necessary to understand what is gross 1 square. This is easy because this is just the number of couples of natural numbers. In fact, we can see this is the first couple, the second, this is the last one. Then here, so we have gross 1 lines, gross 1 columns, and the product is gross 1 square. And so on. We can now write down a lot of different numerals representing different numbers, infinite ones, and to work with them. And pay attention that gross 1 is the last natural number. In the same way, in the set 1, 2, 2 is the number of elements in the set 1, 2, and 2 is the last natural number. So now we are able to see infinite natural numbers. If you have difficulty to accept the existence of infinite natural numbers, this is because traditional numeral systems did not allow us to observe them. In the same way, Piracha do not know about 3, 4, and 5 because their microscope is too simple.